Hello everybody. In this video we will discuss about acetal and hemiacetal formations from aldehyde and ketone. So how would you make it? So let's say you have an aldehyde or ketone. It doesn't matter what you have. You can just replace simply with the ketone as well, so it doesn't really matters what you use. So both of these would react with the same way. So some book write if it's ketone, if you're starting with ketone, they call it hemiacetal and ketol. Some book just stay consistent, hemiacetal or acetal. So it doesn't matter which book you are using. You can just know the difference between hemi and complete. Okay, so we'll go back to our H the way we had. So you noticed, so when we react an aldehyde in acid catalyzed medium, so which means you're going to have plenty of acid, there will be excess supply of H plus ions, and you react with an alcohol. So this is important. So you have excess alcohol and you have excess proton. Then you end up adding this alcohol molecule CH3OH to your pi bond right there. So maybe if you want to add, you can see here, we can show here. It's technically not necessarily the same hydrogen, but just to show you that we removed the pi double bond here and made it single bond. So this is called hemiacetal because you have added one alcohol molecules, right? So you have added one alcohol molecule. Again, you can do the next set of reactions. So usually hemiacetals are not that stable, so the reaction will continue when you have excess alcohol. So where it will replace the OH with OCH3. So if you notice in this molecule, we have added two alcohols. So here, two alcohols are added. The reason we are saying alcohols because this OCH3 here is coming from the alcohol. Okay, and in hemiacetal, you have one alcohol molecule is added. So one alcohol molecule is added. So basically, you can draw the product very easily to find out the reactions. So maybe let's do a quick reaction. So let's say we have a molecules like this. I will draw the mechanism in a second, but let's try to. So we have H plus ions, excess H plus ions, or sometimes it will be written as sulfuric acid, excess H plus, and with CH3, CH2, OH. So in this case, how would you draw the product? So maybe I would color code this. So when you draw the product, so first step is draw this one and convert this carbonyl to OH, and on the other side you add your first alcohol OCH2 CH3. We'll go over in a mechanism in a second. So this is the first alcohol you added across the pi bond. That is your hemiacetal. Hemiacetal. We can keep doing this reactions. So we can add the next alcohol where we're gonna replace the OH with second set of alcohol. So let's draw it out. So we could, now we got OCH2 CH3, OCH2 CH3. All right, so that's alcohol 1, that's alcohol 2. So this is your complete acetal. So this reaction is important because you will see later we will use this method to convert this carbonyl into acetal and use this as a protection group. We will see that later. And then at the end, if you react with H plus with excess water, and if you do that, you will recreate your acetal, you recreate your ketone right there. And On the other side, you're gonna get 2 of the alcohol that's there. So both of this alcohol will be regenerated. Okay, so that's pretty much what happened here. So if you have excess water here, okay, so that's how you can go all this route and come back again. So we will draw the mechanism from here up to here. So let's draw them out. Again, it's gonna be very simple, and keep this method for future reactions. So maybe I will use, okay, so I will use an acetone for this reaction. Again, it doesn't matter what you use. So here, so you noticed, so let's say when you have excess proton, so when you have excess proton, you're gonna have abundant supply. So proton's not gonna be by itself, it's gonna get attached to something else, like it could be CH3 CH2 OH, or it could be it's just gonna attach to a conjugate base. So let's call that HB plus. So this stands for acid, when you have excess supply of acid. Okay, so this is positive, so this proton here is acidic proton. And if we go back our previous knowledge of any type of carbonyl, we know that carbonyl has negative charge, partial negative charge on oxygens and partial positive charge on carbon. Okay, so let's draw that out. So we know carbon has partial negative charge, and oxygen has partial negative charge and carbon has partial positive charge. So in this case, when you draw the arrow, this is where students do mistakes. They draw like this. So this is wrong. So you should always draw arrow from the electron. Okay. So what would happen? So you are removing the acidic proton because you have a lot of acid. Okay. So we got that. Again, this B stands for just the conjugate base. It could be attached to anything, right? So we got CH3, O, H, and then our B is neutralized now. Okay, so B is neutralized now. So you notice here, oxygen has 3 bonds. So if we go back for this whole semester, we have been talking about every time oxygen has 3 bonds, it would make a positive charge. Okay, so it will make a positive charge. So now question is, every single time you create a positive charge on oxygen, your goal should be to neutralize the positive charge somehow. So how can you neutralize this positive charge? Well, there are a couple of ways you can neutralize it. You can neutralize it by getting rid of this proton that you just added, right? So you can say, you know what? I'm positive right now. I'm just going to give up my proton to go back to neutral. So it will bring back the electron again towards oxygens, and the proton will go towards the B. Okay, so you can get back your neutralized, so proton will go with this one. So if you do that, that's basically going backward. That's where you started from, right? So if I get rid of my hydrogen, that's the same thing as the structure before. So you will see in this step, in this mechanism, for every step for this reactions can go either direction. So every step is in equilibrium with others previous step. All right. So in order to neutralize, so why don't I do something different? I will move this pi electron towards oxygens. So if you do that, so let's say I move this pi electron towards oxygens. Okay. So let me delete one of the bond. So you noticed I moved the pi electron towards oxygen. My oxygen is neutral. But you notice one thing here, the carbon atom is not octet anymore. Okay, so the carbon atom is not octet anymore. So to maintain that octet, simultaneously, an alcohol molecule would attack. So simultaneously, an alcohol molecule would attack. So I'm just using simple methanol. So I'm going to redraw back again whatever we did before. So again, we had positive charge on oxygens. So we neutralize the positive charge on oxygens by moving the pi electron, and that would create the electron deficient center. So it makes the carbon atom more electrophilic. So by adding this proton here, it makes the carbon atom more electrophilic. So here the carbon atom is, the C atom becomes more electrophilic when there is a positive charge on oxygen. Okay, so when there is a positive charge on oxygens, the carbon atom becomes more electrophilic. All right, so let's draw the next intermediate that you will be making. So all the steps are going to be equilibrium. So I'm just keeping things consistent. CS3, CS3. Now it becomes OH. And then here we just added OCH3H. So this is called tetrahedral intermediate 1. So this is tetrahedral intermediate 1. Why? Because you notice the carbon atom here is now tetrahedral. Before it was sp2 hybridized, now it is sp3 hybridized. So that's why it's called tetrahedral intermediate 1. One more thing here. So you notice oxygen has here 3 bonds. Every time you have 3 bonds, it should have a positive charge. Okay. Now, what's the next goal should be? Your next goal should be to neutralize the positive charge. And you can neutralize the positive charge by breaking this bond. If you do so, that's basically going backward. Okay, so let's do something different. We can neutralize our positive charge on this oxygens by getting rid of this proton on the alcohol. So we can get rid of this proton here, where this 2 electron would move towards oxygens. All right, and that's gonna be our CS3, C, OH, CH3, and OCH3. So you notice this is our hemiacetal, right? This is our hemiacetal. Okay, so this is our hemiacetal, because we have added 1 alcohol so far. Okay, so one more thing you keep in mind, this reaction is happening in acidic conditions, so you will never see anything that is negative charge, because if you cannot have anything negative, everything's going to be either positive or neutral. So this is how you make hemiacetal. This is also called tetrahedral intermediate 2, because we're going to see 3 of those intermediate. Okay, and what was the one of the byproduct was? So you see the base has abstracted the proton. So obviously you're gonna make Hb plus, because the base is abstracting the proton. Again, that base stands for anything, right? It could be anything. The base could be stands for this. This could be a base. Like anything that could abstract a proton will abstract it. Okay, let's move forward with these reactions. So now you see we have a couple of oxygens here, here, and we have extra proton. So what would happen? Proton and oxygens are match made in heaven, so they like each other's. Now this oxygen can abstract a proton. If it does so, that's basically going backward. But let's do something different. Let's this oxygen abstract the proton. So let's say this oxygen abstract the proton. What would we be making if it happens? So CS3, OH, H, oxygen has 3 bonds, so it should have positive charge. And on the bottom side, nothing changes, OCH3. Okay, so this is called tetrahedral intermediate 3. Okay, so at this point, what is your goal should be? So your goal should be to neutralize the positive charge on oxygen. So how can we do that? We can get rid of our proton and neutralize it by bringing these two electrons, but that's basically going backward. So let's do something different. We're going to eliminate our water. Okay, so we will eliminate water. So just hold on a second. So what would happen if I eliminate my water? So let's say if I take out this water. So if I take out this water, you notice the carbon atom here does not have octet anymore, right? So carbon atom here does not have octet anymore. So in order to maintain the octet, oxygen will immediately donate a pair of electron to bring it back. Okay, so let's bring this back. So these things will happen simultaneously. So this electron would go towards oxygen because you are neutralizing the positive charge on oxygens. And simultaneously, oxygen will say to carbon, oh, carbon, you don't seem happy anymore because you don't have octet anymore. Here, take 2 more electrons from me. So let's draw the intermediate that you will be making after this. Okay, I'm color coding so that you can see where things are changing. CH3, CH3. I will keep the base here just for your sake, and water. So the water could act as a proton source. Water could serve as proton abstractor as well. And then on this side, you have now double bond OCH3. And you notice oxygen has 3 bonds. So 3 bonds means positive charge right there. Okay, so now you have positive charge on oxygens. And that's it. So you started with an sp2 and then you brought back to sp2 again. So you notice this structure is pretty much similar with this structure. So what would happen? What should be your next goal? Your next goal should be to neutralize the positive charge on this oxygens. And how would you do it? You will bring back those pi electrons, and simultaneously the second alcohol molecule would attack on this carbon atoms. Okay, so simultaneously it would attack. So CH3, CH3, O. Okay, this is OCH3. This was our first alcohol. The second alcohol now become OCH3H. Again, oxygen has 3 bonds, so it should have positive charge. And what's your next goal should be? You try to, so again, this is, you try to neutralize this. So you try to neutralize this. And how would you do it? Your base would abstract the proton. So base means anything that can abstract a proton. The B would abstract the proton. And bingo, we got our product. OCH3 and OCH3. And then we got BH plus. So you notice we started with BH plus. And we started with BH plus and we ended with BH plus. So it's acting as a catalyst. And in the meanwhile, we created hemiacetal. So this is alcohol 1, this is alcohol 2. So we added 2 alcohol molecule to our reactions. Okay, so this is your acetal. Because we added, this is your first alcohol we just added, this is our second alcohol that just get added. Okay, so that's pretty much all about the reactions. We'll do another example here. So what if you have something like this present? Not theirs. So what if you have something like this present in excess. So what would you be making here? So draw the hemiacetal portions. So the hemiacetal portions would look something like this. So you noticed our CO becomes OH. And then maybe I should color code this portions. So you're going to connect one of the alcohol here. So oxygen is the one that is being connected, right? So you got oxygen, one carbon atom, two carbon atom, another OH. Okay, so this is where a lot of students did mistake. Okay, so the reason I'm drawing like this is for a reason. So the next set of alcohol, people do this mistake. So remember, we can replace this OH with another OH. The common mistake people do this type of product is they draw like this OH and they replace another one like this. But the likelihood of this, there is another OH right there. The likelihood of this attacking this and replacing is a lot more high than another giant molecule come in and replace the OH, right? So the likelihood of this OH replacing this OH is going to be pretty much higher than another whole molecule come in place there. So instead of doing this, the correct answer would be, obviously you can make some of the side product, but the more likelihood product would be, it would look something like this. So you got oxygens, okay. Then we got carbon atom 1, carbon atom 2. There's another oxygen here, and then this would be replacing. So this is how it would look. And if I do a few more reactions, let's say excess H plus with water, I can regenerate back my ketone again. I can regenerate back my ketone again. I'm sorry it took a little bit way too long. This video is a little bit longer, but this is a very critical information, so I took a little bit longer. Okay, and obviously you're gonna make the byproduct, which is alcohol. Okay, uh, that's it. So this is a cyclic acetal, and you can have those as well. Let's do one more practice problems, and I want you to have your answers on your own. So what if you have something like this? Plus, just keep an eye on how many carbon atoms we have. Okay, this picture looks ugly. Okay, there are 3 carbon atom, 1, 2, 3 between 2 oxygen. So when you draw the product for here, it would, so this is what you had. First intermediate would be, it would look something like this, OH, and then you attach O, and then you got 3 carbon atom, right? So we're gonna 1, 2, 3. So you guys see 1, 2, 3. Then there is OH, and then this OH would serve as the second alcohol molecule to replace it. So you will end up, so you got O, O, and you see 1, 2, 3. We got 3 carbon atom in between. This is where a lot of time people mistakes. So what if I take this and react with excess H plus and water? If I do that, I will regenerate back my ketone, and I will also regenerate my alcohol. Again, 1, 2, 3 carbon atom, OH, OH. So that's how you can convert back and forth between acetal. So this is a cyclic acetal. All right. Okay, let's stop this video here.